Welcome back, everyone. Let's get started with day 23 of MAT 2150, covering chapter 5.2. Today, our topics will include exponential growth and decay, and as an application of integration, we will integrate those exponential and growth decay models. So let's first talk about the technique that we will use in order to compute the integration of some of these models. In particular, we will need integration by parts. And here I'm going to introduce the idea of the chart method for integration by parts. On the left side of the chart, we pick the U. On the right side of the chart, we pick dV. Here, I want to differentiate 2x and integrate e to the 2x. That means that my u is 2x and my dv is e to the 2x. Now, the next row of my chart, I will differentiate to get the next level. We'll compute the derivative over here, and we compute the integral over here. The derivative of 2x gives us 2. The integral of e to the 2x gives us 1/2 e to the 2x. And now we're going to add one more layer to my chart. If we differentiate again, we get a 0 here. And we get 1/4 e to the 2x here by integrating one more time. So ordinarily, before we would say our answer is given by uv minus the integral of v du. But observe here that that is exactly this multiplication. Here we have uv minus the integral v du would give us this row, which actually turns into this multiplication by these two. So let's write down our answer with our old formula here and make sure that our chart gives us the correct answer. Reading this off of the chart, we have u is 2x and dv is e to the 2x dx. That means that du, the next row, gives us 2 and v gives us 1/2 e to the 2x. So now our answer here is u times v minus the integral of v du. That is 2x times 1/2 e to the 2x minus the integral of 1/2 e to the 2x times 2 dx. So now we can simplify this one, and you can see we get our answer. Let's simplify it. 2 times 1/2 cancels here, and we get x e to the 2x minus 1/2 e to the 2x plus our arbitrary constant c. So now let's read our answer right off from this chart. We should get the same answer. Now, to keep track of this minus, I'm going to go down the left-hand side of my chart with a plus, minus, and then a plus. Now, this box times this one gives us x e to the 2x. Here I've canceled the 2 and the 1/2. Now we have minus 2 times 1/4 gives us 1/2 and e to the 2x. And now since we have a 0 in this box, we know we're done with our answer. So we can add our arbitrary constant c. You can see we got the same exact thing. But with the chart method, it really speeds up the process and gives us a way to write down the answer in a much more efficient manner. Let's try one more example here with a more complicated term. If you try this one with our previous method, then you will indeed have to do 2 integration by parts before you'll be able to write down the answer. Doesn't sound like much fun. So that's why we want to use our chart method. Again, we pick our u over here and we pick our dv here. I'll pick u as 2x squared and the dv is e to the 2x. Now we compute derivatives down this left-hand side until we get to 0. Let's see, the first we'll get 4x, the next we'll get 4, and next we finally get to our 0. So now let's do our integrations. We first get 1/2 e to the 2x, 1/4 e to the 2x, and then 1/8 e to the 2x. Now, starting in the top left corner, start with a plus, a minus, a plus, and then a minus, corresponding to the minus VDU term in the integration by parts formula. And now we read our boxes across these diagonals. So let's write down our answer. This box times this box. We get 2x squared times 1/2 e to the 2x minus 4x times 1/4 e to the 2x plus 4 times 1/8 e to the 2x, and then plus our arbitrary constant c. And lastly, we can simplify this to get x squared e to the 2x minus x e to the 2x plus 1/2 e to the 2x plus our arbitrary constant c. And then, of course, we could simplify this further as x squared minus x plus 1/2 all times e to the 2x by factoring out that common term, and then we add c. Let's even try an even more complicated example to really run into the ground the idea of why we need this method. Now, if we have this cube power, we would need 3 integration by parts in order to write this one down. But with our chart method, we can do it really quickly. We have u over here and dv over here. Let's pick u as 2x cubed and dv is e to the 2x. Then we get 6x squared, 12x, 12, and finally 0. Over here, 1/2 e to the 2x, 1/4 e to the 2x, 1/8 e to the 2x, and finally 1/16 e to the 2x. Starting here, go plus, minus, plus, minus. And we read our box across the diagonals to write down our answer. Let's see, 2 times 2 gives us 1. So the first term is x cubed e to the 2x. Now we have minus 6/4 is 3/2 x squared times e to the 2x. Now we have plus 12/8 let's see, divided by 4 gives us 3, divided by 4 gives us 2. Let's see, what term are we on here? I got lost. First term, second term. Now we're at plus 12 over 8. And there's an x. Well, we can simplify that at the next step. E to the 2x. Now we're on the next term. Minus 12 over 18. E to the 2x. Now we've gotten to our last row where there's a 0 here. And so we can add our arbitrary constant. Now let's do the simplification here. 12 over 8 is the same as 3 over 2. And 12 over 18 is the same as 2 over 3. And we have our answer. Let's try one more example here. Using our chart method, on the left, let's pick u is x to the 4th. On the right side, let's pick dv is equal to cosine x. Now we can compute the derivatives down the left-hand side until we get to 0. 4x cubed, 12x squared, 24x, 24, and 0. Now here the antiderivative of cosine is sine. Repeating that, we get minus cosine. Now we get minus sine. And finally, we're back to cosine, and then to sine. Now we read our answer off of the diagonals with the correct sign, a plus, a minus, and a plus here. Now let's write down our answer. X to the 4th sine of x. Minus with a minus makes a plus. Four x cubed cosine x. Now plus with a minus makes a minus. 12x squared sine of x. Minus 24x cosine x. And plus 24 sine x, plus our arbitrary constant c. Now let's get to our applications. First, recalling the basic future value models, which tell us how much money will there be in some account if we start with an initial amount for a given time period and a given interest rate. Our exponential model says the future value or present value will be given time by the present value, the starting amount, times e raised to the interest rate, k, times the amount time t. So then our future value, if we started with the initial amount of 200,000, we have a growth model here, so this should be a positive KT. E raised to the interest rate, which is 5% written as a decimal, and then we multiply that by the amount of time, 4 years. Now, of course, you can do the calculation, plug this into your calculator, get a decimal, and round that to whatever value you need. Make sure you're careful when you do the rounding. So now let's think about how do we go in the opposite direction? We're given the future amount, and we want to find the present value, the initial amount in the account, so that we ended up with $200,000. That means that we have 200,000 is equal to the initial amount times e raised to the 0.04 interest rate multiplied by 4 years here. And so that gives us the initial amount must be equal to 200,000 divided by e raised to the 0.04 times 4. Or we can think of this as 200,000 times the multiplication of e raised to the negative 0.04 times 4. And then again, we can use our calculator to find the decimal. So now let's think about our growth and decay models when we have an accumulation of a continuous income stream. What this means is that we have a rate of income. Like R of T could be your annual salary, or the portion of your salary that you place into a savings account. And that is per year. So if we are continuously adding every year the same amount of money, or a function which could increase, say we could increase our contributions to this account every year, and it's accruing continuous interest, then how much is accrued over a certain amount of time is given by this formula. This formula says that we add money to the account and it accrues interest, and so we can find the future value as this integration. Of course, if we have a constant function, say if we add only the same amount of money every year, the same amount, then R of T is a constant function, and that simplifies to this equation here. And so let's show that step. Let's show if that R of T is a constant function, then we do indeed get this formula. So let's say here that R of T is equal to, let's say, C. This is the amount that we add to the account per year. Then our integral simplifies a little bit. Instead of R of T, we can have C here, and then we're integrating e to the minus kt with respect to t. So now this constant can come out front in front of the integral sign. And we get e to the k times t, capital T, times our constant c, times this integral, e raised to the minus kt dt. And now let's integrate this with a u substitution. We'll say u is equal to, let's say, k times t. Then du is equal to k dt, or du divided by k is equal to dt. Now we have e to the k times t times our constant c. It's given by our new integral, where our new bounds will be 0 to k times t, e to the minus u, and du divided by k. So let's put that 1 over k here, and du here. Now this constant can come out front. And now we can do our integration. The antiderivative of e to the minus u is minus e to the minus u, and we evaluate that in between 0 and k times capital T. So we have kt. Let's bring this minus out front. It's minus c over k. Now we can do the evaluation. We plug in the top bound, e to the minus k times t, and then minus one. Oh, where'd my e go? There should be an e to the kt there. Now let's clean this up. Here we have this minus. Push that inside here, and let's multiply by e to the kt. Let's see. Let's do this multiplication first. Minus c over k. E to the kt times e to the minus kt gives us 1. E to the kt times 1 gives us e to the kt. Now we can push this minus inside, and we get c divided by k times e to the kt. Now this is the positive term. We put this minus inside, and then we'll have a negative 1. Now lastly, we can recall that r of t was our function that we called c, a constant. So we end up with r of t divided by k times e to the kt minus 1, which is exactly what we see here. Now this is the case when we have r of t is a constant function, and the case where r of t is not a constant function, then we'll have to use our integration by parts and evaluate with the first formula. So let's do an example where we apply this. Here we have an account where we are going to add a constant $300,000 per year. We want to know how much money will be in this account after 25 years if we also have a 6% continuous interest rate. Here we have a constant, r of t, which means that we can use our formula For the constant case, plugging in our information, we have R of t is 300,000, K is 0.06, and we have e to the 0.06 times 25, and then minus 1. So again, I'll let you think about the calculation and the rounding. Next, we'll introduce the idea of accumulated present value. We can think about this as the amount of money we would have needed to start in with our account, given that we're adding money to this account for a certain amount of years and it's collecting continuous interest to have the current amount that is in the account, or to have the amount that we desire after the future time. So how much money do we need to start with? So let's see. Let's think about this equation. This would be our constant case. And if R of t is not a constant, then we have the integration case, where we need to use integration by parts. Let's show this formula. We'll first start with our previous formula, with our equation that we called number 5 here. We're assuming that R of t is a constant. Let's work backwards and solve for the amount of the principal balance, which will give us continuous interest equal to this amount. Let's write that down as an equation. So we start with what we just called equation 5. That is assuming the constant case. Then our accumulated future value is given by this quantity. And so now we want to choose our B so that B times e to the kt is equal to A. So how much money did we need to start with, the principal amount, to apply continuous interest and to get this accumulated future value? So now connecting the dots, that says that B e to the kt is equal to R of t over k times e to the kt minus 1. Now we can divide both sides of this by e to the kt. Now we can simplify. On the left-hand side, we get a cancellation. We also get a cancellation here, but we'll need to account for that term. Let's write it carefully. So we have B is equal to R of t divided by k times e to the kt over e to the kt minus 1 over e to the kt. Now again, get a cancellation here. We end up with just a 1 there. And we can say B is equal to R of t over k times 1 minus e to the minus k times t. Gives us exactly the formula that we were after. This is the case when R of t is a constant, and for the case when R of t is not a constant, then we apply this formula. Let's try an example here where we find the accumulated present value. Here, our R of t is 233,000. T is 17 years, and we have an interest rate of 3%. So we take B, and that's set it equal to 233,000 over K, which is 0.03, times 1 minus e raised to the negative 0.03 times 17. And then we can use our calculator to find the decimal, then to round it however we need. Now let's try an example where we have a non-constant accumulation. That is, our R of t is not a constant function. Here this says that we're going to start with 400, and then after each year we're going to add 8% more. So let's see. Now that we have a non-constant, income stream, we need to use our integral formula in order to find the accumulated present value. So now we take our integral. Our t is 10 years. R of t is 0.08 t plus 400 times e raised to the negative 0.08 t, and we integrate with respect to t. Here I'm going to organize our integration by parts with the chart method. We'll take u as 0.08 t plus 400 and dv as e raised to the negative 0.08 t. Then du is 0.08, and differentiating one more time gives us 0. Now integrating, we get 1 over 0.08. That is, we get negative 12.5. And now integrating one more time. It gives us 156.25 e raised to the negative 0.08 t. Now let's remember our plus, our minus, and we read our answer off of the diagonals. So now let's be extra careful with our signs. We have our negative here, 12.5 times 0.08 t plus 400 times e raised to the negative 0.08 t. Now next term, we have minus 156.25 times 0.08 times e raised to the negative 0.08 t. And now this will be our last term since we have a 0 on this row. And we evaluate this in between 0 and 10. That means we plug in 10 everywhere for t, and then we subtract when we plug in 0. Let's simplify it a bit first. This is negative 12.5 times 0.08 t plus 400 minus 156.25 times 0.08 and now all of that times e raised to the negative 0.08 t. So now we can plug in 10, negative 12.5, 10 times 0.08 is 0.8, minus 156.25 times 0.08 times e raised to the negative 0.8. Now we subtract. When we plug in 0, this term will be gone. So we have negative 12.5 times 400 minus 156.25 0.08 and then times e to the 0, which is 1. Now we've done the evaluation. All that's left is do the calculation, which I'll save for you. Now for our next example, we want to find the accumulated present value and the accumulated future value of a position where we have someone who starts working at 35 years of age and plans to retire at 65, given an annual salary of $95,000. So let's assume that they are going to invest 100% of this amount of money, and they're going to earn a 5% interest rate compounded continuously. Let's find the accumulated present value. Here we will have a constant income source of $95,000, which means that we can use the constant formula. So our accumulated present value will be equal to B, which is 95,000 divided by the interest rate, 0.05, times 1 minus e raised to the minus 0.05 times, well, if she was 35, and then will retire at age 65, and that must have been 30 years. Next, let's find the accumulated future value. Again, we can use our constant formula. It's 95,000 divided by 0.05 times e raised to the 0.05 times 30, and then minus 1. Next, we're going to consider the growth and decay models where we have the consumption of a natural resource. What we would like to find is how many cubic feet of this natural resource will the world use from 2000 to 2002, assuming that the year 2000 was time t is equal to 0, and the consumption of the natural resource will grow exponentially at a rate of exponential rate of 5% per year. Then the integration from t equals 0 to t equals 2002, or 2 for us, gives us the area under the curve and represents the total amount of the resource used after t years. So for our model, at t is equal to 0, we have 16 trillion cubic feet. So we'll say P naught is equal to 16. Our K is 5%, so we'll say 0.05. And we want to know how much of this resource was used from t is equal to 0 at 2000 to 2002. So our capital T is 2 years. Now, our total consumption will be represented by the integral from 0 to 2 times 16 e raised to the 0.05 times t dt. Now we can do the integration by a u substitution. We can find that we will need a division by 0.05. We get 16 divided by 0.05 times e raised to the 0.05 t, and we evaluate this in between 0 and 2. We can bring this constant out front. 16 divided by 0.05 gives us 320. And now that's e raised to the 0.05 times 2 minus e raised to the 0, which gives us 1. So now our output here, I'll let you do the calculation, gives the amount of resource used or consumed between the years 2000 and 2002, and that's in trillions of cubic feet. This ends our lecture for chapter 5.2. We'll see you next time.